We're going to look at another optimization problem, this one again involving a box, but in this case we're talking about the cost of making such a box. So it says we want to construct a box whose base is 3 times the base, whose length is 3 times the base width. The material used to build the top and bottom costs $10 per square foot, and the material used to build the sides costs $6 per square foot. If the box has to have a volume of 50 cubic feet, determine the dimensions that will minimize the cost to build the box. All right, so we're in the end, remember, we're going to need to come up with a cost function here. So first let's draw this box. So this is my best attempt at drawing a box. Okay, that should work. And then it says we want the box's base length to be 3 times the base width. So that allows us to write this in terms of one variable. If this is the width, then since the length is 3 times that, I should call that 3x. So now I only had to use one variable for that based on that information. But of course, there's no information about the height, so I'm going to have to make up a new variable for that, maybe h. All right, so now let's talk about what the total cost of this box is going to be. So, cost. Well, I'm told that it costs $10 per square foot to build the sides, and to build the bottom and the top. So that means that this and the bottom here cost $10 per square foot. So let's figure out the total square footage of the top and the bottom, and then we'll multiply that times 10, and that should give me the cost of the top and the bottom. So the top and the bottom, well, each has area of 3x squared, so together they'll have area 6x squared. So just to get you a sense of, that this is actually going to give cost, I'm going to put in units. That's feet squared. And then since it's $10 per square foot, I'm going to times that by $10 per square foot. And then you can see that those cancel. And of course that was the top plus the bottom. Let's move this over. Okay, and now I need to add in the cost of the sides. And according to the problem, it says that the sides cost $6 per square foot. So let's get the volume of these 4 sides. Now you're going to want to be careful here because it looks like the front side and the back side have area of 3xh. And the 2 sides in this picture would have sides xh. So 3xh, 3xh for the front and the back, and then xh and xh for those. That makes up a total of 8 xh's. So 8 xh feet squared. And then again, it's $6 per square foot, so we're going to be timesing that by $6 per square foot, and those cancel. And so that gives me the sides. And so then my cost function is going to be multiplied out 60x squared plus 48xh. Alright, so we're kind of well on our way, but our cost function is in terms of 2 variables, and we want it to be in terms of 1. So I'm going to try to replace that h. So that's where you go back to the problem, and you note that they told us that the volume of this box has to be 50 cubic feet. So the volume of this box in general is going to be 3x times h. So 3x squared times h, and we need that by the constraint of this problem to be 50. So solving that for h gives me 50 over 3x squared, and that'll allow me to make this substitution. And then it'll allow me to write the cost in terms of one variable, plus 48 times 50 over 3x squared. So this is where I might cancel a little bit. 48 divided by 3 is 16. And when you multiply 16 times 50, you get 800. So this is 60x squared plus 800 divided by, oh, and I forgot the x there too. So there should have been an x in here. And one of those will cancel with this guy down here. So I get that. So there's my cost function. So that was all the modeling step. But I got my function. We'll talk about domain. Well, x can't be 0 if you look at the cost function. So it has to be bigger than 0. And then I guess after that, if you just look at that function, there's no other real restrictions, right? You're not taking the square root of a negative. That's the only time you're dividing by 0. And I guess that means in theory that you could make a you could make a box that's really not cost efficient at all by just making x really, really big. And so this would be a really long but short box, but it would probably cost a fortune. So the only restrictions, as we just to summarize, is that x needs to be bigger than 0. All right, so now we actually solve. All right, so we need to take the derivative of this function. Again, I would recommend writing this as 800 x to the negative 1 when it comes time to take the derivative. So c prime of x would be 120x minus 800 x to the negative 2. And for critical points, I'm going to set that equal to 0. And now I'll solve this by adding 800x squared to both sides. So now I've got 800 over x squared is equal to 120x. And we'll cross multiply to get 120x cubed equals 800. And 800 divided by 120 is, so we'll just move it over here. Actually, let's move it all the way up. So that means that x cubed is 800 over 120, which is 80 over 12, which is 40 over 6, which is 20 over 3. So x cubed equals 20 over 3, which means x equals the cube root of 20 over 3. All right, so let's confirm that we've got a minimum here. So I'm going to make my number line, starts at 0, goes on in theory forever, and that's x, and this is our cost, the derivative of the cost, and this is the cube root of 20 over 3. So we're going to have to get a sense of what the cube root of 20 over 3 is. If you have a calculator, you might just plug it in. It ends up being in between 1 and 2. It's like 1.882. So that means to ensure that we've got a min, I'm going to plug 1 into my derivative. And when you plug 1 into the derivative, you get 120 times 1. I guess I'll plug it into this version here. You get 120 times 1 minus 800 over 1. That is a negative. And when you plug in, 1,000, 120 times 1,000 minus 800 over 1,000 squared is basically 120,000 minus a really small number. So it's positive. So we know we found a min, which we wanted because we're trying to minimize the cost. All right, and so that means that we can interpret now. And so that means that we're asked for the dimensions, right? The dimensions. So the dimension should be, the box should be x by 3x, so that means cube root of 20 thirds, and the units here are feet. Feet by 3x, so 3 of those, feet, by, and then I guess I gotta find the height. So let's go to our height relationship. And the height is 50 over 3x squared, so that's 50 over 3 cube root of 20 over 3 squared. And I mean, we can, since I guess I'm leaving out these answers all with radicals, I guess we'll just leave it like that. It might make sense in a problem like this to actually plug these into your calculator. And maybe I'll just do that for you in a second. But this is 3 times the cube root of 20 over 3 squared feet. And I think that ends up being just to note, the cube root of 20 over 3 is about 1.882, and therefore the height, if you plug that in, is about the height would be about 8.856. All right, so I guess it depends on what your teacher wants, but I would accept this answer. It's precise. All right, and so again, on the next slide, I'll just show you another function. I'll show you the cost function, and we'll see that the minimum happens exactly where we found it. All right, and here's our cost function in terms of x, and then we see that 1.882, which is the cube root, that's the same as the cube root of 20 over 3. There is where the minimum cost would occur. And then if it asked for the actual minimum cost, we would plug in, and we would get this.